Okay, so this video will be split up into 3 different parts. The first part we're going to look at is how to calibrate the legs and the servos. The second part we're going to look at is after we calibrated the servos, how do we find the inverse kinematic equations associated with those angles? After we do that, we will look at the code. I'll go through everything step by step, and here is a demo. So I'm using a Desmos graphing calculator. Here's 2 vectors starting at the origin. This will represent the leg. This point right here is the femur joint. This is the tibia joint. And this is the femur joint. This is the tibia joint. And this is the end effector, which is the foot, basically. So for example, if we want our leg to be in this position right here, we can enter in, let's say, 0, and then this number right here. So 113, negative 119. Space negative 119. Now when I press enter, the leg should form a position that looks like so. Now I'll press enter, and we can see the leg forms an angle or a shape that looks exactly like so. So for example, if we want the leg to extend outwards, we can input a coordinate, which will be 0, and then around 370, and negative 120. Once we input this here, we can press enter, and the leg should move and form a shape that looks like so. We can see the leg moves and forms like a shape like so. And keep in mind that this point right here is the origin. This is 0, 0. So if you look at it, this is slightly below the origin, which is exactly what's happening here. And one more example, if we want the leg to be up here, we can go, let's extend quite far. Let's go like this. So we can do a 0, and so 390 and 144. So let's go 150. Now when I press enter, it should enter a shape that looks like so. And we can see it forms a shape like so. And we're gonna go over all the code, all the inverse kinematics, and everything starting now. Okay, so now let's take a look at the calibration of the servos. Sorry, I have all the 3D printers running, obviously, because, yeah. So here, I'm going to open a new sketch. And in ChatGPT, I'm simply going to write servo turn to 90. I don't have to write a single line of code because I don't know how to code, but that's okay. So we can see here, we have the code. Just copy this code, paste it in Arduino IDE. Now we can attach our servo. So we're gonna be calibrating this new leg right here. For the coxa joint, we wanna calibrate it to 90 degrees, obviously. So what I need to do is actually unscrew some parts here. And now from here, we can detach the servo horn from the servo. Okay, so now that we have the servo horn detached from the coxa servo, and the leg is able to free spin, and the servo horn is actually able to spin by itself without any interference, now we can connect the 3 lines. We can connect brown to ground, red to live, and yellow, which is connected to blue, which goes to 9. And right now, how I have this laid out is the live all goes to the live on a breadboard. The ground all goes to the ground on a breadboard. This is okay for testing. If there's any heavy load, it's not good. The breadboard actually burned right here because these lines are, I don't even know, like I think they're 22. So they can't handle a lot of amps and they'll heat up and everything will explode. But I just plug them into my LiPo battery, which is very dangerous. Be careful doing it. And once you have your code, you should be able to run it. Okay, now I can very, very carefully, and making sure I do this right. So this right here is ground, and I'll connect ground to the the black. And then this is live, and I'll collect the live. I'll tap it a little bit, make sure nothing burns, everything's good. So now what I like to do, now making sure my Arduino is plugged in, I can just go here and click run. Once I click run, and this code right here, well, all it does is the servo is attached to number 9, pin number 9, and it'll write the servo and turn it to 90 degrees. So now that it's successfully compiled and uploaded, we can go back here and just being careful, what I like to do is just tap it, and then the servo, get this in view, the servo here, this will turn to 90 degrees. So, tap it, and the servo turn to 90 degrees. After it's done that, what we can do is let go of the power. We don't need the power anymore. Now this is the coxa. We can put the horn back on and try to center it, go better, and try to center it so that it's straight out in line with the coxa. So not like this, not like that, just like this. Just get it as well as you can. Usually with the 25T, which is the standard size, it's easier, but these are actually 18T, so they're actually quite a bit harder to center. If you can't do it exactly, it's okay. So just as centered as you can get it. So this is around as center I can get it. It's a little offset, but it's okay. We can fix that in the code if we need to later, which is not really a big of a deal. Now we can screw everything back in for the coxa. Here, I'll just put in 2 screws right now, but you're supposed to have 4, but it's okay. There we go, just like so. Now, we've calibrated this servo to be at exactly 90 degrees. Well, not exactly, but it's close enough. Okay, now going back to the code, we need to calibrate the femur and the tibia. So we can go to my servo attach 9, let's leave that how it is, and my servo right. We'll change this number to 0, obviously, pretty simple. This is my femur servo, and this one is connected up, the yellow is connected to yellow. The yellow is connected up to yellow, and the yellow goes all the way over here and it connects to number 5. Okay, so the connection doesn't really matter that much, so we want to change this attach right here to number 5. Now that we've done this, we can run the code. Once we ran the code, we need to disassemble everything. We need to make sure that this servo is free spinning, the femur servo that we're trying to calibrate. So here's a screw. Okay, now that we unscrewed everything, we should be able to pop this straight out, like so. And now, this femur servo is able to free spin. And now we can go back, and we just ran this code, so all we need to do is plug in the battery very carefully. And we can see that this servo turned to 0 degrees. And how we want to line this up is, it doesn't really matter actually. Sorry, this servo just turned to 0 degrees. I didn't catch on frame, but how you want to line this up is actually, it does not matter, like I just said, but how I did it was I lined it so that it's straight downwards like this. I aligned it so that it's straight downwards, and you can just plug it in like so. There we go. And then now let's go on and figure out the tibia servo now. Okay, so this is my tibia servo, and we can see it's connected. It's not connected actually, so let's connect it up. Okay, now it's connected, and we can see the black, which is attached to the brown, which goes to this, which goes to white. The white goes to ground, so this is good. And yellow attaches to yellow. Yellow goes to purple, and purple goes to number 3. Okay. So now on our code, all we need to do is change servo attached to number 3, and we want to keep this the same. We want it to go to 0 degrees, and let's run the code. Run the code, it's compiling, blah, blah, blah. Once it goes successfully, we can turn back here. Okay, now we need to pop this out. So pop this out. So now that this is free spinning, we can just set this in place, but let's just keep it here for now. This should turn to 0 degrees once I plug in the battery. There we go. Now it's at 0 degrees. Now what we can do is extend, this is how I've calibrated. I can extend it straight out like so, just like that. plug everything in, and then screw everything in place. Okay, there we go. We'll just do this for now, and everything should be aligned properly now. Now that we got this done, we can go over to the inverse kinematics equations and work on those. Okay, another thing we want to keep in mind is, since we know that this angle right here is 0 degrees, so on our leg, we can write that this right here is 0 degrees, meaning that this right here will be 180 degrees. And right here, this hanging straight down is 0 degrees. So we know that this angle right here is 0 degrees, meaning that this right here is 180 degrees. And for this coxa joint, out is 90 degrees, so know that this is 90 degrees, facing towards us will be 0, facing this way will be 180, which is what I've drawn here. This is 0 and this is 180. And that's how we want to label a graph, and then we can start calculating the angles based on this. Alright, so now that we have the servos calibrated and the legs calibrated, we can start finding the inverse kinematics. Let's write down our goal first. So our goal is to be able to input a x, y, z, and for it to output a theta 1, theta 2, and theta 3. These are the angles of the servo in order for the servos to turn, in order for the leg to reach this given x, y, z. So that is our goal. So how do we do that? Now we have the relative angles. Let's start off by defining our origin, which we'll define here, 0, 0. Let's start with the relative angles. The relative angle for this, how we calibrated it is, this is 90 degrees. That's how we calibrated our servo. So this is 90 degrees, meaning that this is 0 degrees, and this is 180 degrees. Now let's take a look at the femur. The femur, we calibrated the bottom, the leg being straight down as 0 degrees. Therefore, this is 180 degrees. Taking a look at this tibia, we know that we calibrated when the leg is straight out to be 0 degrees, and therefore, opposite to that, we're directly across from that is 180 degrees. So now that we have this information, we can go ahead and start labeling our theta 1, theta 2, and theta 3. Theta 1, actually before we do so, let's draw some triangles and draw some stuff that we know. From this line to this line, from the tibia to the femur rotation, center of rotation, is A. From the tibia servo to the foot, let's call this B. And let's finish this triangle so we can use a law of cosine or law of sine later and call this C. We know what A and B are. They're given. A is equal to 200. For you, it may be different, obviously. B is equal to 300. And C, we don't know. We also know this length right here, from here to here. This is the length of our coxa. So L is equal to, in my case, it'll be 62. Now that we have this, we can go ahead and draw another triangle right over here. This is a right triangle. Now let's define the horizontal distance from the origin to the tip of the foot, which will be this entire distance from here all the way over here. Let's call this R. So this is L, and let's call this D. Now, let's pretend the leg is not completely straight. This will make everything easier. If the leg is not completely straight, for example, it's turned this way a little bit. And for example, let's pretend this is the tip of the foot. It goes all the way out to the tip of the foot. Therefore, this line, which is the hypotenuse, will be R. The same thing as this, the horizontal distance from the origin to the foot. Now that we have R, we can draw a line across like so, connecting against the, let's also set our axes. For example, looking at this angle, let's call the vertical axis here, let's call it Z. The horizontal axis here, we'll call it Y. Looking at this, the horizontal axis will be Y, which is the same as here, and the vertical axis, this is X, and this is negative X right here. This is quite important. Now we can draw a line from the tip of the foot to the X-axis, and this forms a right triangle. Now let's define our theta 1, theta 2, and theta 3. Our theta 1 will be right here, this angle. If the leg is turned right here, this will be theta 1. If the leg is turned right here, our theta 1 will be this. So theta 1. Now let's define theta 2. Theta 2 will be the angle from 0, which is here, to the angle of the femur, which is here. So it will be from here to here, which will be theta 2. Now we need to calculate theta 3. Theta 3 is angle from here to here. Angle from 0 position to the tip of the foot. The angle of the tip of the foot, which is theta 3. Now that we have theta 1, theta 2, and theta 3 defined, let's start calculating what theta 1, theta 2, theta 3 is in terms of x, y, and z, or a function that's in terms of x, y, and z. Let's take a look at theta 1 first. Theta 1 is in a right triangle. When we see a right triangle, we should think of SOHCAHTOA. And the tangent of theta 1 is equal to the opposite over the adjacent. The opposite being this, the adjacent being this leg right here. The opposite is our y-axis. So this is y. Our adjacent is x. So tangent theta 1 is equal to y over x. In order to solve for theta 1, we can take an inverse of both sides. So arctan, which is inverse tan, arctan of y over x is equal to theta 1. Now if we take a look at this, what happens if x is equal to 0? We get division by 0. That's no good. So in coding and in mathematics, we can do a two-argumented arctan. Arctan, and in code we would write it as a tan 2 y comma x. This is very, very good, because what this gives us is, say for example, we give it a point. Let's give it 1, 1 in the xy. 1, 1 will obviously be right here, which will be 45 degrees. So this will output 45 degrees. Now for example, if we need it to be over here, this will be negative 1, 1. Negative 1, 1. That's the input. We put it in here in terms of x and y, right? The output will be 135 degrees, which is 90 plus 45 degrees, which will be out here. And that's the angle the servo will give us. Basically, this ensures that there's no division by 0, and it correctly knows the quadrant you're in. So this is very, very helpful. But in code, we need to turn this from radians to degrees. We'll do that later, because Arduino and other stuff, they only calculate it in radians. So we can figure that out later. So let's box this up as one of our equations. Now let's go over to theta 2. Theta 2 is made up of two different angles, one from here and one from here. This will be alpha and this will be beta. Let's start off with calculating theta 2. Theta 2 is equal to alpha plus beta. Now that we have this, and this makes sense, we can calculate alpha and beta. Let's start with calculating alpha. So we can see that alpha is in another right triangle. So in this case, we can do a tangent alpha is equal to opposite over adjacent. Opposite is d. D over the adjacent. This adjacent right here is a z. But this is actually a little bit different than this case, than theta 1 case. This z right here is a negative z, because this is the positive direction and this will be the negative direction. So very important that we put a negative z here. If you don't do this, it's not going to work. And this is one of the mistakes that I made in my previous video. So tangent alpha is equal to d over negative z, the opposite over the adjacent. And like what we did before, we can also do a two-argumented arctan. So take a tangent of both sides, and then so alpha will be equal to a tan 2, and this will be d common negative z. Now we have alpha, we have one component, we need beta too. Let's solve for beta now. So we want to solve for beta, so therefore we want to look across this angle and we see that it's b. So we can do b squared is equal to two adjacent side from the angle we're trying to solve for, which is a and c, a squared plus c squared minus the two adjacent sides times 2, 2ac, times cosine of beta, which is the angle we're trying to solve for. And we can solve for beta by doing b squared minus a squared minus c squared is equal to negative 2ac cosine beta. Now we can divide both sides by negative 2ac. Doing this, we'll get a squared plus c squared minus b squared all over 2. Positive 2ac will be equal to cosine beta. So beta is going to be equal to inverse cosine, our cosine, of a squared plus c squared minus b squared, all divided by 2ac. Now that we have this, we have our alpha and we have our beta. So now we can calculate theta 2. Theta 2 is equal to alpha plus beta, and alpha is a tan 2 d comma negative z, plus our beta, which is a cosine a squared plus c squared minus b squared, all over 2ac. Now we have our theta 2. Let's box this up. Now let's continue to find theta 3. So theta 3 is a supplementary angle with this right here. Let's call this gamma. What this means is theta 3 plus gamma is equal to 180 degrees. So in order to find theta 3, we can do theta 3 is equal to, subtracting gamma on both sides, we get 180 minus gamma. So we can see that right now theta 3 is in terms of gamma. So we need to find what gamma is. And we can see that it's in the same triangle, so we can use another law of cosines. So doing a law of cosine, let's look directly across from this angle. We see c. So we can do a c squared is equal to two adjacent sides, which is a and b, a squared plus b squared, minus 2 times 2 adjacent sides, the 2 adjacent sides, which is a and b, times cosine gamma. Doing this, we can solve for gamma now. So c squared minus a squared minus b squared is equal to negative 2ab cosine gamma. Dividing both sides by negative 2ab, we get a squared plus b squared minus c squared, all divided by 2ab will be equal to cosine gamma. To solve for gamma, we can do an inverse cosine on both sides. So gamma is equal to our cosine of a squared plus b squared minus c squared, all divided by 2ab. Now that we have this, we know what gamma is. But keep in mind, our goal is to find theta 3. And we know that theta 3 is equal to 180 minus gamma, which is a cosine a squared plus b squared minus c squared, all divided by 2ab. And this is our theta 3. Now let's go back to theta 1. Actually, no, let's go back to theta 2. The mistake I made is when this is completely straight out, this is kind of hard to explain, but when theta 1 is equal to 90 degrees, meaning that this leg is straight out like this is in line with the y-axis. Therefore, we can call this y right here. But only if theta 1 is equal to 90 degrees. But once it moves, it becomes a hypotenuse, and it's not in line with y. So instead of calling this y, we need to call it a different variable. In this case, I call it r. What this allows us to do is calculate r. R is equal to, we can see here, right triangle Pythagorean theorem. R squared, right here. R squared is equal to the two legs squared added together. So r squared is equal to x squared plus y squared. Therefore, r is equal to square root of x squared plus y squared. This is another equation that we need. Now let's go through everything and find if we can solve for each one. Theta 1, a tan 2 yx. Y and x is given, therefore we can solve for this. Now let's try to solve for theta 2. A tan 2 d comma negative z. Negative z is given. What is d? Let's take a look. D is this right here. And we can see here, this plus L, D plus L is equal to R. So we can write D plus L is equal to R. And what do we need? We need D. So let's solve for D. So D is equal to R minus L. This is another equation we need. D is in terms of R and L. We have R and L is given as a constant, which is the coxa length. So now this term is good. Now let's take a look at a cosine a squared plus c squared minus b squared over 2ac. All of those terms are given, I think. A is given. C is not given, actually. So we need to also solve for c. So in order to solve for c, we can look here. C is in another right triangle in this case. So we can do Pythagorean theorem. C squared is equal to the two sides, which is z squared, technically negative z, but once we square it, it's positive, so we don't need it right here. Z squared plus d squared. So what is c? C is equal to square root of z squared plus d squared. This is another equation we need in order to solve everything. And to make sure we can solve for c, c is in terms of z and d. Can we solve for z? Yes, that's given. D is also given. It's not given, but we can solve for it based on this equation that we have here. So now we know that this equation we can solve for, this equation we can solve for. Now let's take a look at theta 3. Theta 3 is 180 minus a cosine of a, b, c, and we have a, b down here. So a is given, b is given, and c we just wrote equation for, so we can also solve for this. Now this is our inverse kinematic equation solved for, and obviously these variables here. Now let's check this with what I had earlier. So one mistake I made, which I pointed out, is the negative z. And yep, everything looks correct. Yep, it looks like I did it right. So now the next part what we're going to do is we're going to take all the inverse kinematics we solved for, put it in Arduino code, put it in code, and I'm going to have a way for you to test to see if the angle that it outputs makes sense or doesn't make sense. So we're going to go do that next. Okay, so let's go over all of the code now that we have all our inverse kinematics. Everybody skips over this part. They just go straight to the robot working. And like I don't understand how they got from here to making the robot work. So we're going to go over everything. And we're going to look at all the code line by line. The first line, hashtag includes servo.h. This library includes the servo library, so we can control the servo motors using attach and write functions. Without this, the code won't recognize the servo functions. The second line, include math.h. This includes the math library, which provides functions like square roots and the two argument artan and the a cosine used for inverse kinematics. Now we need to talk about this block right here. This right here is servo objects, basically. It's like setting variables for each servo. We'll later use this to, we'll later use like coxa servo.write to move the actual servo itself. And I have some comments here, pin 6, pin 10, and pin 11. I'm not using pin 9, which you should probably use pin 9 because they're all in a row, but I'm not because it's kind of broken on my Arduino, so yeah. This next block right here is defining the leg link lengths. So I just set A equal to 200, B equal to 300, and L equals 62, which I have right here. Obviously, you can change these numbers, and I put a constant, meaning these values won't change. So A is also the, let's see, yeah, A is the length of the femur from the from the femur joint to the tibia joint. L is the length of the coxa, which is, some people call it the coxa offset because they have their origin right here, but I have my origin right here, so I just call it the coxa length, which is 62 in my case. And B is the tip of the foot to the tibia servo, which is 300 in my case. Actually 303, but it doesn't really matter. 3 millimeters, like, Not gonna really notice that much of a difference. You can obviously, I can just change to 300 if I want to, but I don't really feel like it. All right, so void setup. So yeah, so these separate setup functions, they only run once we start the Arduino. And serial.begin, this let's starts a serial communication with your computer. And I'm pretty sure it's like 9,600 bits per second, which let us type the coordinates and print the results. Printing the results is actually it's quite important, so we can troubleshoot, and I'll show that in a minute. Coxa servo.attach. So I have the coxa servo attached to pin 6, the femur attached to pin 10, and the tibia attached to pin 11, like stated here. And serial print. This just sends like a message to the serial monitor for me to enter the XYZ coordinates. You can just type whatever here, it doesn't really matter. You don't even need to type anything, to be honest. You don't even need this, to be honest, I don't think. And then we can do end setup and then start the void loop. So this loop, this first if serial.available, this will check if we typed something into the serial monitor. And now these next 3 lines is they will read the next 3 numbers, XYZ, as floats from the serial input. Example, if we type 100, 100, 100, we will assign x equal to 100, y equal to 100, and z equal to 100. But 100, 100, 100 probably won't work. So, yeah. And knowing which numbers to type in, x, y, z, to help us with that, we'll do a inverse kinematics and Desmos, and I'll show you that in a second. And then we can wait 10 seconds, or not 10 seconds. We can wait a short delay to make sure the reading is stable. And then once that has been done, we can clear anything left in the serial input to avoid confusion on the next input. And that's what this does, the clear buffer. So now we can start with the fun part, the not very fun part for typing. The floats, a bunch of floats. So this is just pretty basic. This is just it's all the equations we calculated. So we can call d equal to square root. So this code is actually, the variables are a little bit different. So just take this d, make it this one right here. Pretend d is r and r is d. That's all the difference there is. So we can just switch d and r. That's all. That's the only difference. So float. So right here, this calculates the distance from the origin to the foot in the xy plane, which is r. So that's this right here. From this point right here, the origin, to the tip of the foot, which is r. From the origin to the tip of the foot, which is r. So that's a basic distance function, right? Square root of x squared plus y squared. And we also have, it's basically just like the total reach of the foot, I guess you could say. Now let's, what is this? This is D actually in our case. This is D. This is the horizontal distance from the origin to the tip of the foot minus the coxa offset. So minus L, which is 62 in our case. And that's this equation right here. And then C is the direct distance from the femur to the foot. Yes, it's the direct distance from here to here. That's the C, which is square root of z squared plus d squared, but they have r here. I mean, I wrote r here because when I did the calculation for this code, it was my last attempt, but it's correct. I corrected the code and everything should be right. And one thing to make sure is we need to put them all in degrees, because if we don't, it's going to be in radians and the servos will be confused. So in order to put everything in degrees, it's pretty simple. You just multiply by 180 over pi. And I mean, here you just type in our equations. So theta 1 is equal to, let's just take a look. Theta 1 is equal to a tan 2 yx, right? This is in, if we give it, say, 1, 1. This can be x equals 1, y equals 1, right? What happens is it puts it in here, and then it calculates and then throws out what, like pi over 4, 45 degrees, right? So we need to take that pi over 4, multiply by 180 divided by pi to make it in degrees. Now, once we've done that, it should make sense for the servo. So for this theta 2, we have a tan 2, r comma z, which just replace all the r's with, just pretend r's are d's and d's is r's. It's not that hard. And this negative z is really, really important, because if we don't do this, it's going to act up all weird. And this right here, we want this also in degrees, so we do 180 divided by pi. And remember, I'm pretty sure this is like alpha, and then this right here is all beta right here. So we need a inverse cosine of a squared plus c squared, which is over here. A squared plus c squared minus b squared divided by 2a times c, yeah. And then this is in radians also, so we need to take that and multiply by 180 divided by pi to turn it into degrees. So theta 3, which is right over here. Theta 3 is 180 minus, so this is in degrees, so obviously this is calculated in radians still, so we need to turn that into degrees as well. So it's going to be our cosine a squared plus b squared minus c squared, a squared plus b squared minus c squared, right? That's right. Divided by 2ab times 180 divided by pi, turning it into degrees. So print. So now this just prints, what is that? It just prints each angle to the serial monitor. This is really important. If we don't have this line, it would technically still work, but if we don't have this line, it's very, very hard to troubleshoot. This is almost like this is almost doing what a simulation does. Because if something goes wrong, about the code, and then you plug it in, your servos, like, especially with my servos, I'm using 170 kilogram centimeter servos, or like 17 newton meters. If something goes wrong, your servo's gonna blow. Like, the leg is gonna like go all wonky, and then it's probably gonna explode, right? So what we can do is we can print out the angles and check to see if they make sense before we even plug in the servos to test it on the servo. Now, lastly, this code is pretty important. So this moves the servos to the calculated angles. This is pretty much the most important part. So some of this, so this is three things basically. This constrains the angles within 0 to 180. And the second thing it does is if it's an angle that's a negative degrees, like -5, it'll take that angle and put it to 0 degrees. If we somehow make it, if the angle is over 180 degrees, like say 200 degrees, it'll take that 200 degrees and convert it to 180 degrees. Because if we have an angle, most hobby servos, at least mine right now, you want to choose 0 to 180. Usually you can also go 0 to 270, but a lot of people say that's bad because you're technically spreading out the, you're spreading out the steps into larger ones, but that's not really it. You probably won't notice the difference that much, but right now the servos I'm using go from 0 to 180, so we need to constrain it to 0 to 180, and if it goes beyond that, we need to change it to 0 or 180, because if you don't, the servo might explode. It'll stall and then pull a lot of amps, and then it'll probably burn, and then you're probably gonna cry because it's gonna explode. And it tells it to write. So it just tells it to move to those points. Now what we will do is actually plug in an Arduino, and I'll show you how to troubleshoot. And to see if it makes sense before you even plug in, okay, so before you even plug in the, before you even plug in the, what's it called? So let's see, COM5, run this, hopefully it works. Oh my gosh, it worked. Okay, great, nice. So before you even plug in your servos, you want to see if it makes sense, okay? So I have here, I typed in inverse kinematic desmos. You can use whatever. You can literally just draw on a piece of paper if you want to. It doesn't really matter. Let's use this one here. So let's make this make sense, right? Let's make this 200. A is 200. B is 300. And now let's drag this to a point that actually makes some type of sense. Somewhere right here. So pretend that this joint right here is the tibia, the femur joint. This is the tibia joint, right? We can move this all around here, blah, 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 everywhere. That the green line doesn't go like that. It's fine. We can move it anywhere here. So let's, for example, to test if this code makes any sense, we'll just start at an angle like this. Now we can open up basic and we can see the XY. Technically, this is not XY for us because this is the XY coordinates plane, but our coordinate is actually a YZ, I think. Yeah. Yeah. So what we can do is, let's just right now, we need to focus on one thing at a time. Let's just focus on the Y and Z. The X is most likely going to be right because the coxa servo is only one line of code and it's pretty easy. So we can just type 0 for now to isolate the variables, right? So we know what's wrong if it is wrong. So 0, and then we can just type this in 100, negative 150, 100, negative 150, 105, sorry. So when we type in this, it'll give us it'll give us three different angles. So when we typed in 0, that completely makes sense. Whenever it's 0, the cox angle is 0. It's 90 degrees. That makes complete sense because essentially x is 0. So theta 2. So now we need to take a note of these two angles right here. Does it look like these two angles make any sense? So from here, we know that this is 0 degrees, and we can see here 0 degrees. This is 180, this line right here. So we can see that this actually does make sense because this is 90 degrees right here. This x-axis will be 90 degrees. From here to here is 90 degrees. We can see that this is above 45 degrees, a 45 degree angle. So it'll be 90 plus 45, which is 135. So we know that's going to be greater than 135. And here we can see that it's greater than 135. So that's good. And now let's check this angle right here. This angle looks pretty similar. So we know that this is 0. And so this line extended straight up would be 0. And that angle to here, that looks like around 168, 170. That's right. So the thing we want to check is isolating variables, right? Let's take this line and let's move it out this way. So what do we notice when we move out this way? Looking at this angle right here, when we move it out this way, we can see that this line actually is the slope actually the slope decreases. We have a smaller change in y over the same change in x, right? So what we can see here is that since the slope decreased, we'll have an angle here that's less than, it should be an angle that's less than this. And let's make this around like this. So this looks like 45 degrees, right? So this should give us an angle of around 135. And now let's take a look at this angle. So it went from here to here. We can see that this angle actually also decreased. So let's type in these points and see if both of these angles decrease. If they do, and they're around what this is, so this should be around 90 degrees and this should be around 135. If we get something like that, then we're good, right? So let's type that in. So we can type in 0, and then 316, and negative 102. So let's see what we get. So yeah, this is pretty close. So we can see here this is 90, which is obviously good, and this is pretty close to 135, and there may be slight error somewhere, but it's pretty close. And this right here is, so both of these angles decreased, and I said this one needs to be around 90, a little bit greater than 90 because it's not fully 90 degrees, I guess, and this one should be around 135, which it is, so that's pretty good. So 135 might be like right here, and then 90 would be like this, maybe somewhere around here. So let's type that in. 0, 352, negative 72. So now let's see. Yeah. Oh my gosh, what is that? Why does that look so wonky? Well, yeah, okay, so yeah, we did decrease this a little bit, but yeah, it's pretty close. And now we can test we need to also test the coxa joint, right? So that the coxa joint, so basically if you're looking at this, like if, for example, if I can just open up Fusion. So we see something like Okay, so if we're looking at this from the top view, this right side right here is a positive x, this is negative x, and this is y, okay? So x, y, just a standard xy coordinate plane. So if we did a positive x, say like 100, right? It'll go in this direction. So if we did 100 and then some numbers after it, we should see the angle to be below 90 degrees. So let's check for that. So we did 100 and then because this will give you a positive x, so meaning it'll be somewhere around here. So it'll be angled like this. So that'll be, and we know that from right here where my mouse is, this is the 0 degree. So it's actually getting closer to the 0 degree. So it'll be less than 90 degrees. So 100 and then let's take a look at this most. So we can go 400 where just, yeah, 400, negative 100. And we should see, now we're looking at the coxa joint, we should see an angle less than 90 degrees. And yes, we see an angle less than 90 degrees, which is very, very nice. And if we go above 90 degrees, I mean, if we go negative in the negative x direction, so negative 100, 400, negative what? Negative 100, we should see an angle that's greater than 90 degrees for the coxa. And we see that here. So now we confirm the code is working. Now you can actually go ahead and plug in your servos, barely plug it in, make sure that nothing burns, you don't smell anything, you don't see anything, you don't feel anything burning, and then you can fully plug it in after that, and then it should be working. If there's any questions, you can obviously, I don't know, just ask me. I'll probably answer, probably not, I don't know. If I see it, I'll answer. If I don't, just ask me again and I'll probably see it. So yeah, so we went over all the code. I'll probably put all the links to everything here. Like I can just put this entire code in the description or something. I mean, it's not like I wrote it. ChatGPT wrote it, so it's not like, and besides, I'm gonna open source everything eventually, so it doesn't really matter. So good luck, guys. If you have any questions, just ask.